Good evening. My name is Kawinde Oji. This is group 30, and we're going to be taking you through contrastive and non-contrastive self-supervised learning techniques. So I'm going to first break down the title. Contrastive learning is when a model can be able to differentiate between, it can be able to tell the difference between, for example, let's say, it can tell the difference between a cat and a dog. Yes, they both have four legs. They both have four limbs, but it can be able to tell the difference between the two. Then self-supervised learning. Supervised learning is when data the model uses labeled data in order to interpret information and all that. It uses a labeled data set. So I'm going to take you through the definition of self-supervised learning. Now, self-supervised learning, on the other hand, compared to the other two definitions that I gave you, this is a type of machine learning where the model learns to understand data without being explicitly told what to look for. So here, it's going to use unlabeled data, but it's going to be able to label the data for itself. Like, it doesn't use labeled data, but it's able to do the labeling itself using the knowledge or the data set that it has. That's why it's called self-supervised. It does it itself. The model does it itself. So self-supervised learning is categorized into two, namely contrastive self-supervised learning and non-contrastive self-supervised learning. So under contrastive self-supervised learning here, this is an approach with self-supervised learning where no explicit labels are used. So here it doesn't use any labels just as I had mentioned before, but instead the model generates its own pseudo labels using data augmentations or other techniques. Now, what we mean by data augmentations is in data augmentations that the model is able to generalize, diversify the data into different patterns or to show the relationship between different data. And in the data augmentations, it's able to diversify the data set and be able to generalize it. So it improves the efficiency and the performance of the model because it's able to identify different patterns in the data set and use that to build on and label the data itself. So here, like I said, it's a specific approach within self-supervised learning where no explicit are used. But instead, the model generates its own pseudo labels using data augmentations. Now here, we take note that contrastive self-supervised learning doesn't use human labeled data. It requires no labels, but rather it labels the data itself using augmentations to define the positive and negative samples of the data set. So it's often used for pre-training representation that can later be fine-tuned with supervision. Yes. So we go to the next slide. So as I was briefly describing data augmentation in the last slide, here is a definition. So data augmentation is a technique used in machine learning to artificially increase the size and the diversity of the data set. So, like I said before, it improves efficiency and it improves in a model because the model is going to diversify. Data augmentation diversifies the data set, and by diversifying it, it helps the model to know the patterns, to know different patterns and relationships in the data set. So it diversifies the data set and it's able to identify different things using that diversified data set. And then contrastive self-supervised learning is used when we have no labeled data, but want to features. Then the popular contrastive SSL frameworks are SIM, CLR, which uses data augmentations, and I predicted. So when I take you through this, we have SIM, CLR, we have MOCO, which is momentum contrast. We have BYOL, that's bootstrap your own latent, and sway. So here, I'm going to give you, we have seen the popular contrastive SSL frameworks, but I'm going to mainly talk about SIM, CLR, and MOCO. So in SIM CLR, here, I'm going to briefly take you through the steps. Here, the data, here, text, both of them are used image, they are used in lab images. So in the first one, it takes the image and it makes a copy of it. Then after making a copy of it, with applying filters and all that, then it uses a neural network to get, it uses, then after that, it gets data in the neural network and uses that neural network to convert. When it gets the image, creates two copies of it, and it makes random changes. So after making random changes, it adjusts the neural network and creates a new copy, a new unique copy of that image on its own. Then for MOCO, it does the same as SIM CLR, but this time in MOCO, it chooses the memory bank. So it's going to, after getting the image and making two copies of it, it makes random changes to the image, adjusting, recording, and all that. Then this time it will compare that image that it has created, a copy of that image, to the, it will compare the copy of that image to the almost similar images in the memory bank. So when it compares the image to the memory bank, it will ensure to create a unique image, compare it through that comparison from the images in the memory bank to create a new image. So we have BYOL, which is bootstrap your own latent. This learns representations without any negative samples. So in other words, it uses positive samples. And you have sway, which uses clustering instead of explicit contrastive pair. So I'm going to take you through the next slide. On the next slide, you can see it's a code which demonstrates contrastive self-supervised learning. So here for the contrastive, sorry about that. For the contrastive code snippet, the contrastive self-supervised learning snippet. Here it deals with contrastive loss. So in the code, we are going to import all the necessary libraries, and we're going to create a class called sim. It uses this method, the other methods that I told you about. So yeah. So here we have an encoder, which is ResNet. Here we have that encoder, and we have the forward, which forwards the input X through the encoder. So we're going to compute the contrastive loss in this in the second line where we have defined contrastive loss. This part of the code computes the contrastive loss. And then after, we're going to go through a loop. Yeah, so basically this code is about contrastive loss. Since the images, it uses contrastive loss for image representation. It gets the images using, it interprets the images using contrastive loss. So we're going to go to the next, the advantages of and disadvantages of contrastive self-supervised learning. So one of the advantages is increased efficiency, because here the models learn on their own, like they don't need to use data labels. So basically they are training themselves as you, but using data augmentation, like we said before. And it also increases flexibility, like I said before, the model as if it gets labels on its own, so it can do anything, it can use any data set. It's very flexible. Yeah, using both positive and negative samples of the data set, then it leads to improved representation learning, same thing almost, but it leads to improved representation learning of the data set or the images. So these disadvantages is the computational cost. It's very expensive to come up with such a method because here, I believe it's really expensive for the data, for the model to, it's an expensive method for the model to learn on its own, like create its own labels and all that, putting it into action is difficult. Then we require a large batch size. You're going to require a large data set because the model learns on its own. So it can't just learn from one data set. You need a large size of the data set. Yeah, which is a bit inefficient. And then we have the lack of interpretability. Like we say, the code learns on its own, it creates its own labels for the data set. And sometimes the things it does become too complicated, and us as humans cannot be able to interpret them. So finally, for the last slide, I want to take you through the applications of contrastive self-supervised learning. So it's used in image classification for pre-training representations, and it's used in natural language processing by using the BAT style self-supervised learning. And it's also used in EEG-based applications, for example, stress detection without label data. Yeah, EEG-based applications. EEG basically means EEG signals, EEG processing bases on signals. So it doesn't use label data for those. And the challenges faced here, it's difficult to choose an effective data augmentation. Like we know, the model, like I explained before, this contrastive self-supervised learning deals with data augmentation. It labels, it uses pseudo labels based on data augmentations. So you have to be really keen when you're choosing these data augmentations. Otherwise, if you choose one that's not suitable, it's going to cause a lot of chaos in your model. Then made for large batches or memory banks. So here, I said in the disadvantages, we saw this in the disadvantages. It requires it requires a large data set, and memory banks are used by Marco. Yeah. So it requires large batches, which could be hard to deal with because they are really large, and it could create difficulty. Then it represents representation of collapse negative sampling strategy. It could end up getting more of the negative sampling than the positive sampling because it's supposed to be balanced. So this does not give us accurate data. So that's all that I have on contrastive self-supervised learning. I'm going to call on my colleague to take you through the rest. Thank you.
Hello everyone, my name is Cindy Emmanuel, and I'm going to take you through non-contrastive self-supervised learning. And this category of self-supervised learning, this category of self-supervised learning methods does not rely on contrasting positive and negative pairs. Like it is a paradigm in self-supervised learning where models learn representations without relying on explicit negative pairs, like how it is done in contrastive methods. Instead, this one ensures that different augmented views of the same data sample produce similar embeddings while avoiding collapse, where all the embeddings can become identical. And this is often achieved through architectural asymmetry, redundancy rejection, or regularization techniques. Yeah. So let's go to the next slide. the reasons why non-contrastive self-supervised models are preferred over contrastive self-supervised models these are some of the reasons. So contrastive methods like SIM and MOCO require negative samples to distinguish representations. However, this approach has drawbacks. So these are some of the drawbacks. And also, there is no need for large negative samples. Like, since the other contrastive learning relies on many negative samples to distinguish positive pairs, and this can be expensive. Then it's also more efficient in training since negative pairs are unnecessary, so that batch sizes can be similar and memory requirements are lower. Then also, it avoids collapse through other mechanisms that while contrastive learning prevents collapse using negative samples, this one achieves it through techniques like redundancy reduction and architectural asymmetry. So this non-contrastive self-supervised learning solves these issues by learning meaningful representations without requiring negative. We're going to look at the key techniques in non-contrastive self-supervised learning. So we have redundancy reduction, whereby this one ensures that different dimensions of the land representative sorry. So we're going to look at the key techniques in non-contrastive supervised learning. We're going to start with redundancy reduction, and this goal is to ensure that different dimensions of the land representation carry diverse and non-redundant information. So we have methods like decorrelated representation learning, for example, the Barlow twins, now which introduce an objective function that forces cross correlation representations from different views to be close to identify them to the identity matrix. And this encourages each feature dimension to capture independent information while preserving useful structures. But then mathematically, loss functions may involve minimizing of diagonal terms in the covariance matrix of embedding to promote feature decorrelation. Then we also have asymmetry in architectures or losses. So unlike the contrastive learning, this non-contrastive self-supervised learning, it often relies on asymmetric network architecture, all those functions to prevent collapse. So we have examples like momentum encoder, bootstrap your own latent. Now these ones and Simpson, this ones have one network updates via backpropagation, while the other network updates via an exponential moving average. Then typically one network is trained via gradient updates, while the other teacher has momentum updates to provide stable targets. Yeah. So there is like different network architectures and update the strategies to prevent collapse, because if you like upload the same things, it might collapse or upload an error. So we have stop gradient mechanisms, and these ones, the gradients are not propagated through one of the network branches, and this helps to avoid some solutions, for example, identical embeddings. So SIMSAM shows that simply stopping gradients on one branch can prevent collapse, and this forces the model to learn meaningful features other than trivial solutions. Now, for example, is bootstrap your own latent. it uses a stop gradient on the momentum network to prevent collapse and ensure meaningful feature learning. So we have covariance regularization, and it has some techniques like decorrelating loss functions, and this encourages diversity in learned features. Then we have whitening transformation, like whitening loss. White, yeah, this one ensures that learned features are statistically independent and informative. Then we have the variance, invariance, covariance regularization, which is VCRIG. And this one enforces variance maintenance, covariance reduction, and invariance constraints in the representation. Like, make sure that they are the same pace and they are good to go to be used in this technique. Yeah. So I'm going to take you through the next slide. So this is an example of a code snippet in non-contrastive self-supervised learning. This is a Python code that's the Python implementation of a bootstrap your own latent. And then this trains the encoder to learn useful representations without using negative pairs. Instead, so we're going to start with the first line. This one is to define the BYOM module, which is the bootstrap your own latent module. So we have if you're to break it down, there are two networks, which is self.online and then self.target. So this the self.online, it learns representations actively, like it is actively trained to learn these representations. Then self-target is a slow-moving what? It is a slow-moving copy of the online network, like it helps to stabilize the training. Then we have the predictor MLP, which is this one, the self-predictor. So it's applied to only the online network, and it helps prevent the model collapse. Then we have the forward function, the online network, which encodes X. Then it passes the predictor. Then we also have the target the target network, which encodes X, but without the predictor. So after these two outputs are later compared using cosine similarity loss. So then after here, this line, we're going to define the bootstrap your own latent loss, BYOL underscore loss. So here, as you can see, we have read targets, then return to star F cosine similarity. So this one, it computes the cosine similarity between the spread and target. This is the online, then this is the target network. So that is the loss function. Yeah. So it's minimizing this loss, like, means the online network gets closer to the target network, learning meaningful features. Then moving to the next part, this one is to initialize the model and the optimizer. Yeah. So as we can see, we have encoder equals ResNet. The encoder is used as the feature extractor. Then the BYOL model wraps around the encoder to apply online and target processing. Then there's also an Adam optimizer which updates the online network weights. So we have the training groups. This is the training group. So as you can see it here, It loads a batch of images and moves it to the GPU. Then it passes the images through the BYOL. Yeah. So this BYOL, it gives the read and targets. Yeah. Then it computes the BYOL in this line using the this formula here. Then after it updates the online parameters, the online network weights. So this one, this 0, it clears the previous gradients. Then lost it backwards, it computes the gradients for the online network. Then opt.step, this one updates the parameters of the online network. Then we have this other code here, which updates the target network. It's the momentum update for the target network. So as you can see it here, this instead of backpropagation, this target network here, it updates slowly using the online network. Then the update follows this formula here. Yeah. So yeah, I think that's it. So now we're going to the examples of non-contrastive methods. So here we represented our data in tabular form. So we have Cyan. Now this one uses top gradient. Uses a top gradient on one branch to learn diverse representations. Yeah, then it prevents collapse by no momentum and simple design. And this simply means that, like, okay, now let me start with no momentum. Like, it has two identical networks that process two different augmentations of the same image. And one network has an additional predictor head, which transforms the embedding before it compares it to the other network's output. Yeah. Then we have Barlow twins. This method enforces feature decorrelation using cross-correlation laws, and it prevents collapse by what? By redundancy reduction through decorrelation. And it does this by computing a cross-correlation matrix between two views of the same image. And then it optimizes a loss function that forces each feature dimension to be decorrelated while keeping corresponding features similar. Like I was saying, VIC rig. Now this one adds variance and covariance regularization to standard loss. And then it ensures it prevents collapse by avoiding trivial solutions by enforcing feature diversity. So it ensures that the land representations have a minimum variance across the batch, and this prevents collapse to a single point. Then it ensures that different augmentations of the same image map to similar representations, like in Cyan and Barlow twins. Then it also reduces redundancy between feature dimensions, like in Barlow twins. So we're going to move to the next. So we have applications of non-contrastive supervised learning, and one of them is computer vision. This one is used for learning in tasks like image classification, object detection, and segmentation. Now, basically, when you hear the word computer vision, all these things like image classification and object detection, where we pre-train models for downstream tasks like classification and segmentation. We also have medical imaging used in CT scans, X-ray analysis. But then it doesn't require large labeled data sets. Then we have facial recognition. Then now this This one learns robust features without the need for a negative sample. Then we have natural language processing. This one is it is applied in unsupervised text embeddings and knowledge distillation. Now, like sentence embeddings, whereby methods like SYNCIAN can be adapted for learning meaningful sentence representations. Then you also have text classification and summarization, whereby it enhances like in non-contrastive self-supervised learning, enhances pre-trained transformer models in text-related tasks. We also have language model pre-training. Now this one is applied in models like but without requiring contrastive losses. Then we also have biomedical signal processing. Now this one is used in EEG signal representation without learning labeled data. Yeah. And this one improves classification of health conditions from biomedical signals, issues to do with electroencephalography, whereby we use facial features to detect someone's, we can to make some deductions. Yeah. Then we have finance and anomaly detection. Now this one helps us to deal with fraud and helps us to detect scammers. Yeah. So it learns patterns of fraudulent transactions without labeled examples. Then it can also apply in stock market forecasting, whereby it extracts meaningful financial features without contrastive losses. Then also risk management, whereby it identifies like anomalies in financial records and transactions. So moving on to the next slide, we have the advantages and disadvantages of non-contrastive self-supervised learning. So one of the advantages is we don't need negative pairs because we don't need negative pairs, and this reduces computational costs because it becomes more efficient and feasible for small data sets. Then it also works well in small batch sizes. Yeah. And also simpler. This makes it like have a lower computational cost since it reduces memory requirements as compared to the contrastive self-supervised learning. Then it has simpler architectures and losses. Yeah. Then moving on to the disadvantages. So some methods require careful tuning and of architecture asymmetries, and the techniques like stop gradient mechanisms and asymmetry require careful implementation or else you might mess up. Then the risk of representation collapse if constraints are not properly applied. Like it is very prone to collapse. Like if the proper constraints are not applied, these models can learn trivial representations, which can be dangerous in the long run. Then it is also less well explored as compared to contrastive learning. Like most people are used to using the contrastive learning, contrastive supervised learning becomes hard for me to learn this as well. So moving on, we are going to compare contrastive and non-contrastive self-supervised learning methods. So now the objective, in regards to objective, now contrastive learning, like we said, it learns representations by contrasting the positive and negative of samples, while this non-contrastive, it learns representations without contrasting positive and negative samples. Yeah. Then the methodology, it uses methods like this SIMCLR, MOCO, CPC. I think this one uses BYOL and SIMCIAN. In the training process, like we talked about it involves training a model to distinguish between positive, negative pairs of samples, while the non-contrastive involves training a model to predict a target representation or to minimize a reconstruction error. Then also loss function, contrastive, like we said, uses a contrastive loss function. Just for example, this info NCE loss or the triplet loss. While this non-contrastive SSL, it uses a non-contrastive loss function such as the mean squared CM or cross entropy loss. Then also representation learning, whereby contrastive learns representations by contrasting positive and negative pairs of samples, and this helps to capture the underlying structure of the data, while the non-contrastive learns representations by predicting the target representation, which helps to capture the underlying patterns and relationships in the data. Then, in regards to applications, the contrastive is often applied in computer vision tasks like image classification and object detection, while the non-contrastive is usually applied to computer vision tasks, but then it can also be more suitable for tasks that require learning representations without contrasting positive and negative sample pairs. Then also computational efficiency, whereby it can computationally be expensive due to the need to compute the contrastive level loss function, while the non-contrastive one can be more computationally efficient since it does not require computing the contrastive loss function. So let me conclude. Like in this whole presentation, we've talked about contrastive self-supervised learning and also non-contrastive self-supervised learning. So, and we said that contrastive and non-contrastive self-supervised learning are key in representation learning, but then we have contrastive methods like SIM-CLR and MOCO. Now those ones use positive and negative pairs to learn distinctions. And then need large batch sizes. Then we have non-contrastive methods like BYOL, which is bootstrap your own latent. Then since these ones avoid negative pairs by using architectural asymmetry or regularization, and this helps them reduce complexity while managing performance. Excuse me. Then contrastive approaches excel in structured similarity learning, while non-contrastive ones offer simpler training, and the choice depends on computational needs, data properties, and task requirements. So that has been our presentation. Thank you so much for listening.